In this final video of the series, I'll show how to submit the calculation that I created the file for in the previous video. In the folder that I shared with you, there's a submit directory, which has a few of the files for the calculation already. So I'll go over to MOBA Xterm to take a look at them. For a given kind of calculation, you can generally use the same in-car file with a set of reasonable parameters. So one of the choices in the file is the functional. So this second line can be used to select the RPBE functional. The functional is usually selected based on the potential files that you use, which I'll show later. Both the PBE and RPBE functional can be considered to give accurate results for molecules on surfaces, provided that a suitable van der Waals correction is applied. So at the bottom of the file, there's this IVDW tag, and if this is set to 11, that will use the D3 correction. There are a number of parameters for this correction, which are listed below, but these are all commented out, so VASP's default parameters will be used. RPBE stands for revised PBE and is a change that reduces the amount of attraction in the exchange correlation functional. So generally, RPBE is more repulsive and will give lower adsorption energies and larger bond distances, but it isn't necessarily more accurate than PBE. One of the other parameters that's important in this file is the energy cutoff, which I mentioned in the presentation as well. So here, this is set to 450 EV. The default would be selected based on the elements that you have in your calculation. For carbon and similar atoms, the default is usually 400 EV. 450 EV is accurate without being too computationally intensive. And you can check whether this value is high enough by running a calculation with an increased value and seeing if the energy changes significantly. Another important parameter that specifies the accuracy of the calculation is this EDIFG criterion. So this is the force that the geometry will be optimized to in units of EV per angstrom. Generally, this value of 0.02 is considered a reasonable level of accuracy, but to check this, you could again reduce this value to see if the geometry or the energy change. And one other one to highlight is this NSW, which is the number of ionic steps that the number of iterations that the geometry optimization will perform. So you want to set this so that it's not too small, in which case your calculation will end too early and you'll have to run it repeatedly. But you also don't want it to be too large, because if there's a problem with your geometry, you'll just waste the computation time. I also included in this folder the file that I alluded to in my presentation, which has comments writing out what all of the parameters in the file are, specifying, or essentially what all of the important ones are. And one I forgot to mention here is this npar tag, which does some parallelization if you have multiple CPUs, as is the case on Niagara and Cedar and Graham. So the recommendation is it should be set to approximately the square root of the number of nodes. So for this file, I'm requesting 80 CPUs. So I set it to 8 as approximately the square root of 80. And it has to be a number that the nodes can be divided by. So you couldn't set 9, even though that's closer to 80, because it doesn't divide 80. The Kpoints file, for many calculations, you can just use the gamma point. And so it specifies one Kpoint in X, Y, and Z. If you want to check that this value is converged, you can increase it to 2 by 2 by 1, and then 3 by 3 by 1, and so on, to see if your values change. And I have in here a submission file. The beginning section provides some commands to the scheduler or some parameters. So one important one is the time. The maximum is 24 hours. And if you select smaller times than that, your calculation may run more quickly. The number of nodes is also important. That's essentially the number of resources. So 1 would be the lowest. I often use 2 because it runs still within a reasonable time frame. If you're running NEB calculations, this number will need to be larger. And what Mariam had in her file was 4, which would take less time to run, but it may start more slowly because you're requesting more CPUs. This end tasks should be this number times 40, which is the number of CPUs per node on Niagara. You can include your email address and a condition where you will receive an email from the system, the scheduler. The options are fail, start, and end. These are the modules that need to be loaded to run the VASP code. I tested this earlier and it works, so you should now have the right permissions to load these commercial modules and then load VASP 5.4.1. And finally, there's the command once you've specified these things for the scheduler, srun submits this executable, and there are 2 options for this. VASP_gam is used for calculations at the gamma point, where there are some aspects of the code that can make it run more efficiently. If you're using more than 1 Kpoint, then you need to use VASP_std. There's a 3rd version of the executable, but I don't actually know when you would use it. So the other 2 files that we need are the POSCAR, which I made yesterday, so I can just copy that in. It's this one with bromine atoms. And the POTCAR is a little bit more involved because you need to use the potentials that match the atoms that you have in your POSCAR file. So carbon, hydrogen, bromine, and copper. These files are available in this, it's often called a tarball, or this zipped tar file. Tar stands for tape archive, and it dates from back when information used to be backed up on tape. So the tar command lets you work with tar files. And in order to see the files you can specify, so Z is because this file is zipped, which is what the GZ suffix indicates. And T is the command to output the file contents as text. So this can be piped to a file. I usually give it the same name, but with txt. So now with Vim or whatever text editor, you can look at this and you see a bunch of different elements, and there are some different versions of the potential files for different calculations, such as GW. But for what we need, there's only one version of carbon. There are a number of different versions of hydrogen, but we just want the regular one. And for bromine and copper, there are also just the regular ones. So what you will do is, so by selecting something in MOBA Xterm and in Bash in general, then it copies it. So now I can extract the files that I need from the tar file using the X option, and then listing the files that I want to take out. So now you can see these are in directories, and it extracted just the POCR file. So what I need to make is a POCR file that includes all of the other POCR files in order. So this would be using the cat command, hpodcar, so chbrcu, and then this gets piped into POCR file, and I'll give it a suffix to indicate which atoms are in it. And now this I can copy to POCR in my submit directory. So I have the 4 files that VASP needs, and then the submission file that the scheduler needs. So I can go to Niagara and then log in. So I have these sessions listed here to connect. And it just has the remote host and my username. I don't think there are any special parameters there. That one I don't actually need. So you arrive in your home directory, which is indicated by a tilde. And one file in this directory that is useful is this bash rc. So when you log in with SSL, SSH, then these commands are run. So there are some commands to add some directories to my path. And then I have a bunch of useful key shortcuts that I've written for myself. This qdel and qso to show my own jobs rather than having to remember that it's called scancel. And here I have some variables so I can refer to my backup directories to copy files back and forth from home to Scratch. So there's one environment variable. I sent an email about this already, but this moves to your Scratch directory. And I have my own sort of way of naming folders and keeping track of things. I also used alias to write different commands to move to different directories for the different calculations quickly. So I started one for this calculation I want to run. Now I can copy that directory and go to SFTP panel on the side and go to the directory I want to upload the files to. So there's this upload button here, conveniently already in this folder. So I have these now. This is the POSCAR file that I wanted. To check that the POSCAR files are correct, you can use this command grep or grep for title spelled or title spelled in a German way. POSCAR, and you can see these are PAW, PBE potential files. So this L exchange tag in the POSCAR file will tell VASP which functional to use, because in this case I don't specify one. You use the same files for RPVE calculations, but specifying RP. It will give a warning message that the two don't match, but there are the same potential files used for both, so that should just be ignored, as best I understand. So we can see that the potential files match our POSCAR. We have the usual Kpoints file. Here, 8 hours should be enough to run several hundred steps of the geometry optimization. So we can go ahead and submit this. This indicates it's submitted successfully. And if I use the shortcut to show my jobs in the queue, you can see that it's pending because of a lack of resources. So I'll need to check on this later. Through the magic of video editing, my calculation is finished already. So there's different files that you can check during or after the calculation to see whether it's progressing okay and whether it completed correctly. The output that is written out by the command that you submitted is written to this file slurm with your job ID, where slurm is the name of the scheduler. And you can see at the top there's some information that VASP writes out, which says that it's starting correctly. It found the right POSCAR. There is one minor warning message about aliasing errors that I think has to do with the FFT grid. And then there are two messages that it didn't read the wavecar or chargecar files. So if we look at the in-car, this is because this tag iCharge equals 1 is set, which says that it will resume if from those files if they're present. But because these files are quite large, these tags L wave and L charge are set to false. And so these files are not written out because they take up quite a bit of space and they don't speed up the calculation except in the first step. So then VASP starts to do the calculation. The first section is the electronic convergence. So you can see each of these steps and how the energy is decreasing over time until it reaches the criterion that's specified in the in-car file. So it then writes out the energies and does a movement of the ions to relax, to try to optimize the geometry. And then it continues with the next step. So you can see these are getting shorter generally. Eventually, it should get to a point where it takes about just a few steps, and often it runs just the minimum number, which is set to 4. But in this case, the parameters for the relaxation, and yeah, you can see this is getting more efficient at doing the relaxation because the changes will get smaller as the forces become better. So this continues on for a while until if you press Shift G in Vim, you can get to the end of the file. And you can see it outputs this reached required accuracy message, and then the scheduler writes out a bunch of information about the job, most notably the time that it took to run. So in this case, a little over 2 hours. The information about the electronic convergence is written to this file OZCAR. So that's the same information I showed already. And there's more complete information in the outcar file. So initially some of the same information about the calculation setup. You can also look up certain parameters such as the energy cutoff. So if you're not sure about what something was set to, you can search for that tag in outcar. You can also look at the positions after each ionic step. VASP also prints out information for each iteration of the electronic minimization and then the ionic. So you can see here the electronic steps. And then the next series of iterations, and before that is the information at the end of the electronic convergence, including this energy written out with 2 spaces between energy and without. So this can be a useful term to search for to get the energies after each step. There's also this energy correcting for sigma going to 0. There's sigma as a smearing parameter that's specified in the in-car file in order for the calculation to run efficiently. So the sigma 0 energy is what I usually go for. The difference between these two energies should be pretty consistent. So if you're comparing relative energies, they should give the same result. Another useful quantity to monitor are the forces. So here is the force, the highest force on any atom, which is what the calculation uses for the convergence criterion. And you can see in progressive steps, this should gradually decrease. To look at the coordinates of the system throughout the optimization, there are two files that you can examine. The outcar file that has the positions at each step, and also, but there's also this VASP run file, which is smaller. So that's what I'll usually download to look at. So I can, because it has the XML ending, it knows what plugin to use to read it in. And now if I go to VMD, I can see that initially the hydrogens move because they were at the distance of a carbon-copper bond. And another change that happens is that the surface relaxes because I generated it using ASE, using the bulk lattice constant. And you can see that the layers become closer together as you run. And then the position of the molecule should also be optimized. So you can see that it approaches the surface, that it was not too far off with its initial value. Okay, so that brings this video series to an end. Now I could do the other things that I wanted to, which for this calculation, what I plan to do is to put the bromines under the terphenyls to have them be lifted up. The POSCAR file at the final coordinates are written out to the file contcar, which you can see is the same as the POSCAR. So if you needed to continue a calculation, you could copy this to POSCAR and start a new one. If you want the Cartesian coordinates, you can go to outcar and search for the last set of positions and copy this. So one useful thing in Vim is you can press Control V to go into visual block, and this lets you select a chunk of text out like that. The other files, some of them aren't actually all that useful. Some of them are useful when you specify different flags. So I hope that this series was useful to you. You can post on Slack if you run into some problems, or if you have more questions for me. I'll be available pretty much any time to answer those. And good luck to everyone.